So you'll only take notes on that piece of paper that I gave you. You shouldn't need anything else. If there's any other little comments or things that you want to remind yourself of, obviously you can take notes wherever in the world you want. But that piece of paper is all I needed you to have. Because every problem today is a graphing problem. So the goal for the day is to just refresh our memories on how to graph inequalities. And they're called linear inequalities. And we will be graphing systems of these because it's our systems unit. So, I mean, obviously, part of the lesson is just to make sure that you remember how to graph an inequality. But we won't have any one problem that is just dedicated to doing an inequality. But we'll kind of relearn the the process as we go. So I'm going to bring a little graph in so that I can graph along with you, maybe, if I'm not clumsy. All right. Kind of, sort of good. Okay. So you guys will remember this, especially you ninth graders who had this class more recently. This will be fresher for you. But for everybody else, I have to assume that if I were to put a y equals mx plus b that looked like this. I did not put the equal sign there, and I don't want you to either because we're not graphing equations. But if I gave you a y equals mx plus b line like this, I have to, of course, believe that you'd know exactly what to do. You'd go up 3, put a dot, and then from that dot, you'd go down 4, right 3, down 4, right 3, right? Pretty simple when it's already in y equals mx plus b. Because we're not doing equations, we're doing inequalities. This is not going to be an equal sign. It's going to be a greater than sign. So rather than looking for just a set of numbers that makes an equation true, what we're going to do is we're going to look for essentially half of the plane winds up being a solution set. So because I've taught you this before at one time or another, I can breeze through this relatively quickly. So let's get to it. We're going to go up 3 on our first graph and put a dot. And then from that dot, we're going to go down 1, 2, 3, 4, and make sure you turn the correct direction so you don't get yelled at. If you had made the mistake of going left, then you'd make a positive slope and then you would get, you know, made fun of. And then we're going to go down 1, 2, 3, 4, 1, 2, 3. We like to do this as many times as the graph will allow. So kind of just try to squeeze as many points in there as you can. Now, when you grab your ruler and you go to make a line, don't make the line yet. If you could just please uh, give a quick watch to this. I'm going to make a line, but I don't have a tool that will do what I want to do. So my line isn't going to be what I want quite yet. Does anyone by chance remember what I need to do to the line? It has something to do with that. I say it's been a while. Other than one of you or two of you in this room, I was your Algebra 1 teachers. And so I know we talked about this. What I'm going to do is I'm going to take my eraser. You guys don't have to do it this way because you can make dotted lines as you go. But I'm going to go now and make what we call a dashed line or a dotted line. It's not solid. And the implication given, you can do that now with your ruler. The implication that you're giving by making a dotted line is that the points on that line are not solutions to this math problem. So let me show you quickly. I'm not going to do this every time, but I would certainly be remiss if I didn't show you once. So take, for example, this point right here. And I didn't pick it for any reason other than that it's on the line. So what I want to do just to show you is, and what I mean by why the line is dotted is I want to talk about does that point work or does it not work? So what are the coordinates of that yellow point? 3 and -1. So what we're going to do, and again, I will only do this with you this one time unless you want me to do it again, I will. But I want to show you why the line is dotted. If I take those numbers and I put 3 into the math problem in place of x, and I put -1 into the math problem in place of y, I'll get a statement that isn't true. But it's not just like ghetto untrue, like, 5 is greater than 2 or something obvious like that. It's going to be infinitely close to being true. We're going to get something like 5 is greater than 5, or 1 is greater than 1, or -1 is greater than -1. So that's the conclusion here. Let's make sure that this happens, and then we'll talk about why the line is dotted, and why is that an important piece of communication? So quick, easy math. If I take -1 and I put it right there in place of y, the math problem now says -1 is greater than, and then I have to do -4/3 times x, but x is now a number, 3. And then, of course, we assume by 11th grade that you're perfectly capable of tackling fractions. You would see, of course, in this little math problem here, that the 3's just hook cancel out. 3 divided by 3 just goes away. And we're left with -1 is greater than -4 plus 3. Right? Fraction times a whole number is pretty easy when the things cancel. And then we're left with just -1 is greater than -1. So like I said, what we wind up with is a statement of something trying to be bigger than or less than, whatever, itself, which it's not. And that's why the line is dotted. If we were to go through and pick any other point on this line, the green point, purple point, well, that's not the right one, the purple point down there. If you pick any point on the line and plug in the numbers for his x and y, you'll get a comparison statement that is a number trying to be bigger than himself, which of course is false, right? But we agree, like I said, that it's infinitely close to not being false. What would make it true? What would I have to add to make it be true? In the original problem, what could I have modified to make this statement be true? If I added an or equal to, good. And so that's when the line would be solid, is if it has the or equal to. This should be kind of coming back from your memory bank. If it's just a greater than or just the less than, we make the line dotted to show people that the points on the line they don't count. They form a boundary, but they don't count. If we put or equal to, we make it solid to show that the points on the line do count. They're on the boundary, but they're also solutions, okay? So we won't really discuss this at great length anymore after this. That was a couple minutes that I just have to spend to make sure you understand why we do solid and dotted lines. Okay, so if you're looking for something to put in your notes to help you remember so that you don't have to ask this question 40 trillion times, it goes a little something like this. If you have a greater than equal to, or if you have a less than equal to, your line that you graph will be solid. You make a little box here and just use it as a resource, put a highlighter on it, and then we just never have to talk about this again. If you have just a greater than or just a less than, then your line is dotted. And I hope you understand why that is. It's not just a thing that we do because someone told us we have to. We're communicating an idea. The points on the line either work or they don't. Okay? So having said that, that is not the graph of an inequality. That's the start of a graph of an inequality. What we're going to do now is there's 2 ways for me to explain to you what comes next. Here's the most professional explanation I can give you. After this, I'll give you a more ghetto-fied shortcut explanation. You all see this point? I'm going to circle it in white. Why do we love that white point right there? Because it's 0 and 0, and 0 and 0 are the easiest numbers in mathematics to work with. They destroy things. They make things go away. And if I can make things go away, man, sign me up for that. That's less work I got to do. So what I'm going to do is I'm going to take 0 and put it in place of x. I'm going to take 0 and put it in place of y. And if I do that, put a 0 here and put a 0 here, then I get 0 is greater than, what's -4/3 times 0? And what's 0 plus 3? Is 0 greater than 3? No, this is false, right? So because the point that we tested right there is false, it means that every other point on that side of the line will also be false. Take it to the bank, every single one. Your boundary lays down the law. says you're all true on one side, you're all false on the other side. So the default assumption is, well, if all the points on the side of the point that I tested are bogus, then all the points on the side that I did not test are the solutions. And I hope you remember this from the past. That is how you graph a linear inequality. You graph the line that is the boundary, determine if it's solid or dotted, and then shade the correct side. The shorter explanation is this. And I'm very, very cautious when I explain this because, as you'll see later in the lesson, there are math mistakes to be made. But I would say this, we all agree that this sign that I'm circling says is greater than, right? And every one of us in this room has enough of a mathematical sense to understand that when you draw a tilted line, there's always going to be a top side and a bottom side, correct? So greater than, obviously, duh, means to shade above. And that's why we could just shortcut it and shade the top side. But again, as you'll see here in about 5 minutes, that could be a dangerous thing. If you made a human error getting to the final thing, you'll see. So anyways, that's one inequality. That's the next ones are not going to take very long because now we've got the basics out of the way. The other one that I want us to graph on this piece of paper is this. So we're going to do this on the same grid. This is not a new problem, okay? We're doing a system, so it goes on the same grid as the last guy. So where are we going to start that graph at? We're going to go down 3, and we're going to put a dot. And from that dot, we're going to go up 1, 2, right 1, 2, 3. Up 2, right 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3, so on and so forth. If you're struggling with graphing lines, that's going to be a real hindrance for the next week. If you don't do something to rectify, if you suck at graphing lines and you don't do something to rectify that, you cannot pass the next quiz. It's impossible. Because the foundational piece that starts every problem is the creation of the graph. So now I'm going to graph a line. Will this line be solid or dotted? Solid this time for sure. Okay, so I don't have to do my eraser trick and you guys don't have to do your fancy line. And which side of this line will we shade? Above or below? Above. Now, what you're going to learn from this example is that we have some ugliness going on here. You agree? So the answer to a system of inequalities should not necessarily look like this. The answer to a system of inequalities really should just be, let's focus on where the shadings are on top of each other. So having said that, I would ask you a question. I'm going to make a purple X right here. If I'm in that area, you can see that area. It's kind of, you see these two lines where I'm drawing purple, how they kind of come to a corner and they create a region up in the northwest. Is that purple X inside the solution to this problem? No, it's only in one of them. And the same can be said of this purple X over here. And of course, this purple X down here is no good. It's not in either of them. So really, and I'm going to show you this in the next example, our graphs really shouldn't look like this. Our graphs, if done properly, should look like this. And I don't mean to torment you with having to do a whole bunch of eraser work right now, but honestly, this is what a nice, proper inequality system should look like. I don't want a bunch of excess garbage shading hanging around. I just want to see the region. Okay? So that's question 1. Any issues with that? The next ones will go a lot faster. Okay, so let's get on to the next one. That's what it really looks like. And there's way more conversation to be had about why are we doing this. But again, today is just a mechanical sort of skill practice day. So I'm going to clone this page. So our next one I want to do is y is less than 3. And y is less than or equal to negative 5/3 of x minus 2. Again, I threw you a softball here because I got y already by itself. So that's not going to be the case later, but for now, enjoy free ride. What kind of line is that top one? So it's dotted for sure, but it's also more importantly, it's horizontal, right? That's one of those things that we had to take away from our previous experience in math is that if there's only a y, no x, it's horizontal. If there's only an x and no y, it's of course vertical. So let's go up to 3 and draw a horizontal line. And you should be making yours dotted. I, again, have to fudge mine. So I make solid, and then I bust out some chunks of it to make it look dotted like this. Now, I'm going to show you something this time that I want you to do, and you'll remember this maybe from the first time we had this conversation a year or two ago. And it is that I don't want to shade. What I want to do is I want to draw indicating arrows so that my graph doesn't get messy. This will be really beneficial starting tomorrow. So what I want to do instead of actually shading is I want to draw little arrows that just indicate where the shading would go. And we all agree because it says is less than, that common sense mandates that we would shade below that line. But rather than getting cluttery and messy, just draw a couple little arrows to say, this is where the shading will go. All right, let's get on to the second line. Where are we going to start the second problem at? Down 2, and what's his slope? Perfectly spoken. Down 5, 1, 2, 3, 4, 5, right 1, 2, 3, or conversely up 1, 2, 3, 4, 5, and back to the left 3. Provided we just want to make, we just want to make sure that we make the same tilt either way, right? Down and right is the same as up and left. And this line is going to be solid. Like this. And again, we still need to adhere to basic math expectations. Please put arrows on your lines, right? This is just a thing. It's what we do. They're lines, they're not segments. And which direction would I shade, above or below? Below, because it says is less than. So what we're going to look for now is where do the arrows come to consensus? And so you should now, because you're all pretty bright, you should be able to see that there is a specific region where the arrows press together, right? And you would agree, of course, that that region is bounded where we're below this line, but then we have to take a turn to the southeast and stay below this line. So that boundary that I just drew defines the solution region, and then your solution region should look like this. Any questions about that? Okay, let's get on to example number 3. Like I said, they're not going to take very long from here on out because we've talked about the kind of behind the scenesy stuff. So this one's going to be 4x minus 3y is no more than -9, and bless you, and x is less than 3. You don't have to do them in any particular order as long as they both get done. It's all good. Let's deal with this annoying stuff first. Let's take this top math problem and let's do what we know we need to do. Let's get y by itself. What would we do first? So we'd be left with the -3y is still less than or equal to, right? And what is the right side going to say? -4x minus 9. And then what do we do to finish the job? And what do we remember when we divide by a negative? That we have to flip our Pac-Man, right? So we remember all this stuff. This is just accumulated knowledge from over time. It's kind of what's sometimes fun and challenging about math is that all the stuff you think you never see, and it's like, oh, we saw it again. So we're going to have y is greater than or equal to. Got to switch it when you divide by a negative. What will the slope be? So we have 4/3 of x, and then what will the y-intercept be? So +3. Good. So what we have now is in a purple box, we have a problem that's already ready, obviously, to graph. And then in the green box, we have another problem now that is ready to graph. Everything else on the page, we can really just kind of disregard. So let's get to it. Let's do the purple one first. What kind of line is the purple line? Vertical. Good. Only X is a vertical. So we're going to go right 1, 2, 3. We're going to go, oopsie, I need my line tool. Not the first time that's happened. And it is going to be a dotted, so I have to fudge mine. You don't have to. You could just make it dotted the first time. Which way would the shading go if it says less than? Just follow common sense. To the left. I mean, why would anyone go to the right if it says greater than? A vertical line is the only line in the world that does not have a top side and a bottom side. So this is the only time we abandon that thinking and go left, right. So our shading would go to the left. So we're going to go to the left of this. And again, we're just going to draw some little indicator arrows so that we don't forget. And then we're going to go to the one in the green box. And where will we start our journey on the green box? Up 3, 1, 2, 3. And what's the slope? Up 4, right 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. Down 4. 1, 2, 3, 4. Left 3. 2, 3, 2, 3. And then we make a line. Will this one be solid or dotted? Solid. It's a solid answer.
Will they all be one solid, one dotted?
Nope. It's just happenstance. If that's been the case so far, it's just completely just by chance. So sometimes they're both solid, sometimes they're both dotted. Good question. Where will the shading go off the green line? Up. So now I'm going to sketch in some little indicator green arrows. And again, it doesn't take, I don't think, a rocket scientist to see where the shadings sort of coalesce into one. So using red, I would at this point highlight for you the boundary. There's a turn that happens right up here in quadrant 1. There's where the bend occurs. And you have to follow and respect that bend to say, I got to stay left of the purple line, but also above the green line. And so to make both of those constraints happy, I shade where both will be happy. 3 down, 1 to go. Any questions? You remembering all this? Good. Okay. Last one. We have x minus y is less than or equal to 2. And 5x minus y is greater than or equal to -2. Let's do the top one first. As always, annoying, annoying, annoying. If y is not by itself, I gotta get that done. So how do I get y by itself? Move the x over, which leaves us with -y is less than or equal to -x, still +2, like that. But then you're like, poop, or y is not by himself. What do? We divide it by -1. And because we divide it by -1, we flip. Now, what I'm going to do right now is I'm going to mess up. And I'm going to mess up for a very specific reason. So this is on recording. This is not one of my accidental Ahernisms. I'm going to go like this. You know what I do for a living. I teach high school math. And people are not perfect. And you would have to imagine, listen carefully to what I'm about to say. You have to imagine that there are times that we as humans forget little dumb things like switching the sign, right? So I'm going to go back to what I said in the first example about we have to be careful when we base our shading on the sign that I am circling in yellow. You've heard this speech probably before. If you base your shading decision on that and you forgot to switch a sign, then your whole problem is shot. And that is when, if you're one of those people that's likely to forget to switch a sign, then you maybe don't want, on problems like this where you're going dividing by negatives and doing all this hard stuff, you may not want to make your shading decision based on that. You may want to go back and do it the way I showed you the first time and put 0, 0 into the original problem before your error-prone human hands got onto the problem. But if you are infinitely confident, which you should be, that you would always remember to switch your signs, then feel free always to base your shading on the sign of the final answer. Does that make sense? So there you go. All right, so I'm going to erase this and all my work. And now we're going to tackle this other dork. What do we do with this one? Move the 5x to the other side. Kind of feels like a kind of the same problem over again. So we get negative 5x, a still minus 2 or negative 2. But then once again, you're like, I got to divide by a negative 1. And we remember to switch our inequality sign. Remember, Pac-Man gets the old flipperooski when we divide by a negative or multiply by a negative. Dividing is just more common. So we're going to get y is less than or equal to 5x plus 2. And now the only things on the board that because I like erasing, you probably shouldn't erase, but I just want to focus on these now. These are our finished prize possessions. So let's do the red one first. Where do we start? Down to, what's the slope? Up one, right one, up one, right one. And I don't want to make all these dots. So what I'm going to do is I'm just going to keep tracking my pen and make dots that are really far apart. Will this line be solid or dotted? Good. Okay, so we can leave this one alone. How about the other graph? Where are we going to start the green one at? Up 2, and what's his slope? Up 5, right 1. 1, 2, 3, 4, 5, right 1. Down 5. 1, 2, 3, 4, 5. Left 1. 1, 2, 3, 4, 5. Left 1. Solid or dotted? Solid. So there we are. Let's make some shadings and then let's watch where they coincide. Okay, so off the red one, we agree that since it says greater than, because we remember to switch our signs, that our shading would go above. The green one, because it winds up saying less than, means we have to shade below. Some people struggle with seeing aboves and belows. If you're a person who thinks right and left, you're going to struggle with this until you knock that off. Okay, the only line where you should ever say right side, left side is vertical. Everyone else you think top side, bottom side. Can you see where the shadings coalesce? It's pretty obvious, right? This region right here that I'm kind of wedging in purple, this is where both inequalities are happy. I've got to stay below Mr. Green while also staying above Mr. Red, and that's what it looks like. No, I fixed it. Yeah, I was just messing up by forgetting to switch my sign, but I went back and made it all good. So my mess up was just so I could have a quick talk with you. Any questions? All right. I got a worksheet for you.